should students participate? When I work with the younger students, I see how excited they are. And they, if they're selected a project that they really want to do and they're telling me about it, they're all excited. And when I get to the upper level, sometimes they've lost that excitement. And if you go into a regular classroom, and even talking with my nieces and nephews and their children now, it's kind of like, well, what do you like about science? Well, I really don't like science. Why? It's boring. Science should be exciting. Engineering should be exciting because it's live, it's happening, it's all around them. And we really want students to get back to thinking that it's exciting, and how scientists and engineers actually approach a problem, how they seek the answers to things. And those same approaches that we'll be talking about are applicable to just about anything they do. So it ends up teaching students those lifelong learning skills, the organization and time management. We'll talk a lot about how for you to structure doing that research project with your students. So it's not science fair week, it's the entire semester, and the students receive a grade for every portion of the work they do. That also really helps prevent it from being the parents' project. And I know that's an issue with many people. You feel like, oh, the parents are doing it, the students aren't doing it, so they're not learning what they need. If you do it with each little segment, then it goes back to the students a lot more instead of just the parents.
Judy, this is Manley. Let me jump in for just a second. This also goes with the goals we had in the previous slide, but I want to hear these first three bullets here first. Part of my reason for working with the workshop is to do some activities with you that you might be able to transfer to the classroom. You might not do those exact activities that we do with you in this workshop, but you might do similar activities. And also, I like to try to get you thinking more about the activities that you do with students, and to see if we can get folks to maybe move toward activities that are more inquiry based. You'll understand what I'm talking about a little bit after the next session we're going to do this morning. But that's an important goal. I think we can do a lot more to get students excited about science, whether they do a science fair project or not. So my goal is not so much the science fair project as doing a lot more inquiry and getting students to develop these skills in class. Then the science fair projects will naturally follow because they'll want to pursue their interest in whatever. So anyway, keep that in mind as we go through these slides with you, and I'll get back to this in session 2, Judy. Thanks.
Oh, certainly, anytime. That's what we're doing here. So going back, natural curiosity, Manley was talking about that. If they get excited about something, they're going to follow up on it. And if you're looking at the NGSS, then all of that talks about teaching our students how scientists and engineers approach problems, which we mentioned before. So let's go on. So again, Manley was talking about this a little bit. I think especially when you look at elementary and middle school, there is a lot of going across curricula, and getting the reading and the writing and the content areas are part of doing a good project, because they've got to do background research. They've got to be able to write up what they're finding in their background research. They have to write up their conclusions. You're getting your math in, the analysis of the data, how to best present your data so that other people can understand what you have been able to find, and so that your data clearly shows the conclusions and the analysis that you did, and how your experiment can be translated and affect other things, so, and its value. So the interpretation of scientific data, working in other disciplines within doing a good research project, getting the student interest in that science, also getting the students to really become engaged, encourages them to look at science as a career in the future, and engineering as a career, and technology as a career. And these are the careers that we really need to be encouraging our students to be pursuing, because that's where the jobs will be. The critical thinking skills, when they're analyzing the data, when they're thinking about the steps they need to be doing, are all there. And again, critical thinking is important for our students to have in any discipline that they end up pursuing, to have those real world skills along the way. So There's a process, and I keep talking about the process, and you'll hear me refer to, I am more concerned about students learning that process than to have a mind-blowing project, because the project may or may not, go any further than where it is, but the steps of getting there will stay with the students and help them in the future. And science, but this is the first time I've got science buddies in here. I have, and I will tell you again, a love-hate relationship with science buddies. They have some great information for you. They have some good tools for you to be able to use. They also have a lot of projects listed step by step that students tend to say, oh, this can be my science fair project. And those projects, if it's a step-by-step experiment, that's a verification experiment. That's not independent research. That's not where they're really doing inquiry. So that's all background information. And we'll talk about that a little bit more. But they do have a great time schedule worksheet that you can pull up that talks about each of the steps that we'll be discussing, talks about what's in it, and gives you a suggestion for the number of days to be able to use in doing that one process. They also have rubrics that are on that same set of pages for the teacher tools that you can actually grade each one of those steps so that the students, and I've been in the classroom long enough that if you don't give a grade for something, it's not really important in the student's eyes. So this lets them know that each one of these steps is actually important. And when you're making your schedule, if you think about what your end date needs to be. So who knows what's going to be happening this next year? I mean, we don't even know when school's starting or what it's going to look like. But if you are hoping to do research with your students, and one of the discussions we can get into is how to be able to do some of this remotely. But when you think you're going to be having your school fair or a countywide fair, or local fair, or if it's going to go directly to the regional fair, to look at those dates and then go backwards, to have time for registration for that and time to be able to develop all these different steps. If it's just going to be in your classroom and not moving forward, you want to look at when do you want to have the students presenting their research in your classroom. But remember, if they end up with a really good project, you want to have it ending soon enough so that it might be possible for them to go on to a competition along the way. So when you're looking at that, you need to have the time for the experiments and developing their methods. You need time to review each of those research plans, and that's extremely important, not only for the students, but for you, for your liability issues of knowing what they're doing, making sure they're doing it safely, making sure they're doing it with permissions that need to be done before they begin doing an experiment. They need to have time to put all their information together, to analyze their data, come up with conclusions, and do a paper or a project board. I really encourage putting together a paper, even at the younger grades, because that causes the student to actually look at the whole of what they have done. From the beginning, when they were first thinking about the topic that they were going to work on, to that background research, to the experiment they did, how they did it, what their data was, how they analyzed it, and their conclusions, it pulls it together. And a lot of people don't realize that, but if you are going to a science and engineering fair competition, students are encouraged to bring a paper if they have written one, and they're encouraged to bring their lab notes that they have taken or their journal. And we'll talk about journaling a little bit. It also gives you time to get some parental support. Science Buddies does have a sample letter in there in the teacher tools that you can pull out to help you frame a letter to send to your parents as what you want your parents to help you with, different roles they can do of helping mentor students, answering questions, helping review projects if they have special expertise, providing materials for students that don't have materials that they may need, making contacts with people if they need to talk to a veterinarian or someone else in a specific field. These are all things that you need to try to utilize parents as much as possible, but it also, you need to be letting parents know that this is a student project and not the parental project. You need to have that time that the students are actually going through the processes and the steps that we have, and again, working in time to be present if that's something that's on the docket. The student process looks different because you're doing all behind the scenes work. So they start off, and we're going to have you do part of this. We're going to stop at the conducting experiment and analyzing the results, but we are going to have you do selecting a topic, looking at a little bit of background research, developing a question, and developing a research plan. Because once you've experienced doing it, and we'll talk about them in later sessions and give feedback, some of the things that we see, and that will help you when you're working with students. But the students have to come up with that topic about, and the best thing to do is to have them think about, what are they interested in? You know, what are some of the real world problems that they face? Do they have grandparents that have issues in getting around or doing things, or do they run into another, you know, can they think of another issue or problem that, you know, around the house or that they see in their neighborhood? You know, big world issues are great to consider, but the chance of their being able to solve those is smaller than looking at something that they're really familiar with. But look around them and think of things that they like to do. If they play ball, then maybe they want something to do with that. But again, things that apply to them interest them. If you're doing it as a class activity, then you may want to look at what's out there, what needs to be taught. I used to teach biology. As I said, there were more chapters in the textbook than we had weeks in the year. And that's not including, you know, summers. I mean, there are more than 52 chapters in the book, and I'm sitting here going, okay, we don't have nearly that number of weeks. How am I supposed to cover all of this equipment, all of this information rather? And so that's a point that you can have students look at topics that are covered within the courses that you are teaching, and have them pick out something that they are interested in and find a question in there and develop that and then present that. And that can be a great review tool near the end of the semester, or even during the middle of the year, to bring out information to get the other students interested about something that you may be covering later. But journaling starts from the very beginning. As soon as they start thinking and brainstorming about what topic they need to be working on, that's when they start journaling. If you are a research scientist or a research engineer and you're doing something that may be moving forward to a patent that you would want to apply for, it is extremely important that you have written documentation of every day what was accomplished and have it verified by someone else. I know a good friend who works in a research lab in the Research Triangle Park, and every day, at the end of her day, she walks across the hall to someone in another lab who signs her journal as what she has done and dates it. So there is verification that if there were ever a competition for who gets the patent, they have that information that they can present as evidence as who came up with it first. So the journals should never be crossed out and thrown away. It's, you just keep going. What I did yesterday, I found out didn't work, so I'm changing it and doing this today. So you keep all of that as a background for the students to be able to refer to, or for researchers to be able to use. Selecting that topic, which I think is the hardest part for students to do. We're going to talk about that a little bit. The background research is extremely important once you get a topic, because you have to learn what you know before you can come up with a question of what we don't know. And verification labs and activities are great for students to increase their knowledge, but it is not something that you want to take to a competition, because that's not what they have actually come up with. It's what someone else has done. So that background research builds the knowledge for the student so that they can come up with those unanswered questions or problems. Then they have to develop a testable question, and we're going to work on that in the second session. And they have to develop a research plan. That research plan goes into materials that they're going to be needing to be able to do the activity, whether it's engineering or scientific. exactly what steps are they going to be doing? How are they going to be, and what safety issues are with the project that they are going to be working on. If they're working with humans, you know, in your own classroom, when you take students to do something different, you have to have special permissions, that you have to be careful about what is done in the classroom because of issues of doing experimentation with students. With any human project, there are special permissions that have to be done, and that has to be granted before the experimentation begins. So that needs to be addressed during that research plan. Same with animals, hazardous materials, etc. So any safety issues need to be addressed. The bibliography should also be included in the research plan that shows that you've done some background reading, that background research. And you also need to look at what kind of data you're going to be collecting and how you're going to analyze that data. So once you've developed that research plan, then it's pretty much go forward and get to work. After it has been approved by you or by someone else, it needs to have special approvals if they're working with something that needs that. Then the conducting experiment sometimes only goes for a short period of time, or maybe the experiment will go for months. And if you look at the ISEF rules, those with International Science and Engineering Fair, it states the student can work on a project, do experimentation on a project for a period of up to 12 months within 18 months of their presenting it at a competition. This may come into play this year with students that, as we may or may not be having them in the classroom. So the reality is if they don't start counting that time until they actually begin this conducting the experiment. So all this background work doesn't count into that time frame. So it may be that students that start working on a project this fall may not be presenting it till spring a year from now, and that would still fit within the guidelines. Hopefully for you that won't, and for the students that won't happen, but if it ends up being delayed, then those are, you know, that's a possibility for them. So the analysis of the results, all of this, you have to make sure that you allow time for. And I need to look and see how my time is going. Again, I mentioned before that students don't seem to think that something is worthwhile unless it is graded. So we really encourage you to grade each activity that you assign them and assign different portions along the way. And then that gives you time to review each of those portions to see if your students are on track, or if they're headed in the wrong direction, or if there's safety issues that you need to address. But it also gives them a grade so that they feel that that is important, and you are teaching them the process, not just that you have to have a project that's going to blow everybody away, because everybody's not going to have a project that's going to blow you away. And the reality is it's more important to learn that process. So the feedback that you can give also is extremely important to the students and being able to have a good project. Again, you've got the rubrics that are available for you. So looking at the comparison in scientific research and engineering research, they're similar in areas, but yet they have their own differences. In the scientific research, you look at developing that topic first and finding out what you're interested in along the way, and developing that testable question or the research question that you're going to work on. And you'll have to give one of those before the next session. We'll look at that later this morning. And then during that literature review, to find out more about that topic, more about the question, and that helps you then be able to design the experimentation that you're going, or testing that you're going to be doing. So once you've done that literature review, you've gotten the background information you need, then you can develop that plan for you, what materials you're going to need and how you're going to test it. And for that, the study of design is important. Once you've completed that and you've gotten the approvals that are necessary, then you start actually doing the test and collecting the data along the way. And part of with that study design, you need to know what kind of data you're going to be looking at And again, it comes back to thinking about when you're looking at those research plans, are they only changing one variable? Are they changing 4 or 5 variables? Is this a good plan? And helping the students before they ever get started. The data collection is, if you don't know how you're going to analyze it, then that causes an issue. So you need to think about that ahead of time. Getting that data, again, so that you can frame it so that you can see the patterns. You can see the trends that end up developing in the data and whether or not it's significant, or you need to collect more data to be able to come up with a conclusion, to be able to interpret what's going on. And in most research, what ends up happening is once you've answered one question, you kind of go, that's what happened when I did this. Wonder what will happen if I change another variable or do something else. And so it leads to a continuation, and that's why you're seeing a circle and not just a straight line, because it feeds upon itself. And I have a resource on this slide, and again, you will get these slides later to be able to look at and to be able to use as reference for you. The engineering process is a little bit different. And again, these are overviews. Pretty much the engineering process starts with what we call an ask, which is pretty much like finding that topic. But this time, it's going to be looking at what a need is or a problem that's out there. And as we're looking at that need and the problem, we have to think about what constraints come into our being able to work with it, or being able to solve that problem, or how that answer that we're looking for, the solution to the problem, has to fit within certain parameters in order to be successful. And so the constraints that you're coming up with are really important. Again, same as with the scientific method, you're going to be looking at doing some background research. You have to learn more about what we already know about this problem or about the need that you have to see if we already have an answer to it or if it still needs to be solved. And if it still needs to be solved, then you need to think about imagining, how can I solve the problem? What are some different ways that I can approach it? What are some different solutions that I can come up with? And then you end up coming on one solution that you want to develop. And that's when you plan how you're going to do that. You end up building a prototype or building a model, and then you have to test it, and it's successful. And once you do the testing, you have to think about what is that method of measuring whether or not it's successful or not. Is it going to be within a certain percentage, or does it have to perform 100% all the time? What is my method of evaluation as to whether this works or not? And usually once you build that prototype and test it, you think of things that can be improved upon it. So that create, test, and improve ends up being a mini circle within itself, that once you build it and you test it, you think of ways to improve it, and then you go back and refine that prototype and work on it again. So again, it's a cyclical pattern for both of these, especially in that engineering process. You can continue refining the product that you developed or that solution that you've been working on.